Hello everyone. Today I'm going to be introducing the Fourier transform. Have you ever listened to a beautiful chord on a piano, like the one I have in here, and wondered, what am I actually hearing? So that when you press a single key, like a C, the hammer hits a string and it vibrates, pushing the air around it in a very regular, simple pattern, like a sinusoid. So let me draw one in here. So let's say this sinusoid represents the tone C. We can visualize it. It's very smooth. It's a repeating wave. It's a pure tone. But what happens if now I play E and then I play G? I get similar results, as in if I play E, I will have a similar sign, but that it goes faster. And if I play G, it goes even faster. And then they have their own pitch. They're simple and they're pure in their own. But what happens when I play a C major chord? For those who know music, it's just the combination of all three tones at the same time, like this. Again. So this is what happens. Our ears can pick out the individual notes, but the sound that actually reaches your ear is just one. It's just one complex, messy looking pressure wave that looks like this. So a C chord it looks messy. And because all sounds have been added together, the sound of C, the sound of E, and the sound of G have added up all together to form a complex wave. And it's a complicated signal. They're all mashed together. There's not a defined pattern, and this leads us with a very fundamental problem, not just in music but in science and engineering. How do we take that combined signal, this combined signal that you see here, which is the messy signal, and we break it back down to discover that it was made out of a C, an E, and a G sound? How do we go from the complex mixture to a list of simple ingredients? That is exactly what the problem of Fourier transform solves. So in essence, the Fourier transform is just a mathematical trick. It's like having a function of time that is being converted into the complex realm. Okay, and this signal, this time signal, from the perspective of signals and systems, it could be a sound wave, it could be an image, it could be a radio transmission, it could be a heartbeat. Tells you what frequencies are present in that signal and how strong they are. So it moves us from the time domain, where we can see how a signal changes over time, to the frequency domain, where we can see this recipe of frequencies, this spectrum of frequencies that make up that signal. So in other words, we're grabbing all the signals that are time-based, a C sound, a G sound, E sound, and the C chord sound, which are all time-based signals, and we migrate them into the frequency realm. And how do that looks like? That's what we're going to be talking about in this video. Okay, so for our chords, the Fourier transform doesn't see a messy wave. So the Fourier transform doesn't see the messiness of the function of time. You see three distinct spikes, one for C, one for E, and one for G. It has decomposed the signal. So what we see here, these are function of time, and what we see here, once we apply the Fourier transform, is a function it's a signal as a function of frequency, or omega in this case. So what we see here, instead of looking at a sinusoid, you see peaks. you see spikes. So a spike for C, you'll see it in the negative domain, in the negative side of the plane, and in the positive side. And this represents 262 hertz for C. We will see another wave, another spike for E, and this is a spike that is 330 hertz. Same in both sides of the plane, on the left side and on the right side. If we want to graph G, you will see 392 hertz being placed in here on both ends. And then obviously if we apply a Fourier transform into the C chord, we will see all three spikes together. You will see C sound, the C spike, the E spike, and the G spike, and you will see them as well on the left side of the plane. So 262, 330, and 392. This is the decomposition that the Fourier transform does. And the power of this idea is that it works on anything, not just perfect musical note. It works on noisy signals, on short bursts of sound and non-repeating patterns, which is how the Fourier series is different from the Fourier transform. The Fourier series requires a periodic signal. A Fourier transform doesn't. You can work with non-periodic signals in this case. So we can work with non-periodic signals. Okay, so how does it work? What is the math behind the Fourier transform? Okay, so let me explain this. So let's say we have a function of time, and we want to apply a Fourier transform into it. So we use the Fourier operator, which is just the cursive F. I'm pretty bad doing the cursive F, but maybe you can do something better than I. You apply such transformation on the time signal, and then this will generate the function of omega, which is none other than an integral that spans from negative infinity to positive infinity of the time signal multiplied times a mapping element, which is just e to the negative j omega naught t as a differential of t. Okay, so let me explain mathematically what is happening. So x of t is the signal in time, or in this case the musical note. E to the negative j omega, and this is a typo. This is not omega naught. This is actually omega. So let me rewrite this one more time. So this is negative j omega t. Okay, it's a compact way of representing a pure tone or a rotating phasor at a specific frequency. So it maps all the frequencies. So by multiplying them and integrating them, something similar to a root mean square, the transform is measuring the similarity or the overlap between your signal and the pure frequency. The result, x of omega, or in this case f of omega, gives you the amplitude and phase for the specific frequency omega that we're trying to map out. If the signal has a lot of a particular frequency, then the amplitude or the length of the spike will be greater, as in the frequency is not as dominant. Okay, and if we want to go back, there's the inverse Fourier transform that takes your list of ingredients or frequencies and reconstruct the original, combining all the frequencies together. And to wrap up, that's the Fourier transform, a decoder of complex signals. It allows us to grab whatever signal we have in here and decompose it into the constituents, the different frequencies that compose that complex signal. And with that, we conclude this video.